Hello, everyone. I am Neil Trevett. I'm Vice President of Developer Ecosystems at NVIDIA. I am President of the Khronos Group and the OpenCL Working Group Chair at Khronos. And it's a real pleasure and an honor to be speaking with you here today at RISC-V Days. So in this session, I'm going to start with a high-level overview of all of the compute acceleration standards being developed at Khronos and how they relate to each other and how they might be useful in the context of RISC-V. And then we'll spend a few minutes looking at OpenCL in more detail, including recent developments and the upcoming roadmap. And then I will finish by looking at some recent industry trends in compute acceleration and how Khronos and RISC-V may work more closely together. So firstly, if you haven't met us before, Khronos is an international non-profit standards consortium that is open to all, and all our standards are royalty-free for the industry to use. Our focus is on enabling applications to access the power of hardware acceleration for 3D graphics, virtual and augmented reality, and parallel computation. Last year was our 20th birthday, and we have over 180 members from around the world, including many members here in Japan, from the largest companies through to small startups. But before we get into technical details, what exactly do we mean by standards being open and royalty-free? So we think to be a truly open standard, everyone should have a voice in its creation and evolution, with transparent and well-defined processes to generate genuine consensus, and design decisions about the standard should be made on technical merit with no one company controlling the technology. And free means there is no charge to access or use the specification, and most importantly, no patent royalties to ship products that implement the standard. And at Khronos, we believe that success of any standard is ultimately measured by how widely it is adopted, and that's achieved through adding real-world value to the industry. And also at Khronos, we have come to strongly believe that the success of any standard requires strong investment in its tooling ecosystem. A specification document without conformance tests and development tools is not really a standard at all. It's just a document that will probably soon be forgotten. So why do we need API open standards to access acceleration hardware, including GPUs, and what value can those APIs add to the RISC-V community? So traditionally, as people here know, CPU instruction set architectures, or ISAs, are stable and can be targeted directly by compilers. And of course, the value of the RISC-V ecosystem is being created through the ongoing investment in implementations and tooling for the RISC-V ISA. However, in the domain of acceleration processors, that market is still undergoing rapid and diverse innovation. And so it's not possible or desirable to pick one accelerator ISA in the same way as a CPU. It would be unacceptably stifling to innovation and competition. So APIs provide a level of abstraction above the hardware architectures that can be used directly by applications or libraries or targeted by compilers. And if the industry can agree on multi-vendor open standard APIs, then the costs of developing an API ecosystem can be shared across multiple companies, and software can be portable across hardware from multiple vendors who can bring products faster to market and have full freedom to innovate under the API specification. So I think and believe the bottom line is, if the RISC-V ecosystem wishes to effectively support accelerated applications, then we need both compilers and APIs to work seamlessly together. So what APIs is Khronos working on? Well, here are the standards currently being most actively developed by Khronos. We have a number of 3D acceleration APIs, including Vulkan and OpenCL. We have initiatives around 3D asset formats, including GLTF. We have the OpenXR API standard for portable, augmented, and virtual reality. And on the right-hand side, a family of APIs and languages for parallel computation, vision acceleration, and inferencing, including OpenCL, SYCL, SPIR, and OpenVX. And that's where we're going to be focusing on primarily today. So this is how Khronos standards for parallel computation relate to each other. At the lowest level, closest to the hardware, Vulkan is used for programming GPUs for both compute and graphics. And OpenCL enables software to use any mix of available heterogeneous processors. Both OpenCL and Vulkan provide parallel acceleration of shaders or kernel programs that are compiled to Khronos' SPIR-V intermediate language. And then we have SYCL and OpenVX, shown here on the top row. They are higher level programming frameworks for even more application portability across diverse processors. SYCL enables parallel programming using standard C++, and OpenVX uses a graph abstraction to express vision and inferencing functionality. And SYCL and OpenVX, they can be accelerated by the lower level Khronos APIs, but that is a choice left to the implementer. Let me just give a few more details on a couple of these APIs before we go into more depth on OpenCL. So OpenVX graphs enable a developer to program complex vision algorithms by simply connecting a set of predefined functions or nodes. OpenVX enables inferencing acceleration alongside classic vision functionality and is actually being increasingly used as a portable inferencing engine, including in safety-critical markets. OpenVX accelerates inferencing by defining nodes to represent neural network layers and a set of tensor and tensor operations to represent classes of neural networks typically used in edge inferencing. OpenVX can import a complete trained network in the Khronos NNEF neural network exchange format, imported from machine learning frameworks using Khronos open source tools. NNEF's unique value in the industry is that it provides a stable specification to be directly imported by hardware drivers. The next API is SYCL, and I know we have a presentation coming up, so I won't spend too long, but SYCL is a C++ language framework that uses template libraries to dispatch selected parts of a standard C++ application to acceleration processors. SYCL enables complex C++-based applications and libraries, such as complete machine learning frameworks like TensorFlow, to be directly compiled and accelerated to performance levels that in many cases outperform hand-tuned code. The offloaded C++ code is sent to the SYCL compiler for the targeted accelerator processors, often using OpenCL as a backend, but SYCL is increasingly supporting a wide variety of backends for deployment flexibility. The unaccelerated remainder of the C++ code is sent to the standard C++ compiler for the host CPU. SYCL is gaining industry adoption in a number of markets, including embedded, industry, and HPC, high-performance computing. And for example, the DPC++ language, which forms a key part of Intel's One API initiative, is an implementation of the SYCL open standard. So now let's look at OpenCL in a little more detail. OpenCL is a runtime and programming framework that includes C and C++ base languages for creating compute-intensive kernels that can be compiled and executed across any available processors in a system, including GPUs, DSPs, multiple CPUs, custom accelerators, and FPGAs. OpenCL provides API calls to discover accelerator devices, API calls to compile kernels for selected devices, executing those kernels with explicit control over kernel placement and memory allocation and synchronization, and finally, gather back the results. And when deciding whether to use OpenCL or GPU APIs such as Vulkan, if developers don't need graphics rendering, many of them find that OpenCL provides a simpler programming model, a lighter weight runtime, and more rigorously defined numerical precision that can be critical for many compute applications. So OpenCL is one of the most pervasive cross-vendor open standards for low-level offload acceleration. It's widely used by applications, engines, and libraries, and as a backend target for languages and compilers that need a portable API to reach into hardware acceleration, including Khronos' own SYCL and OpenVX. Most machine learning frameworks such as TVM, Glow, and PyTorch, for example, have OpenCL backends. Also, almost all mobile inferencing engines from companies such as ARM, Qualcomm, VeriSilicon, Synopsys, TI, and Xiaomi use OpenCL as an acceleration backend in mobile and embedded devices. There are additional implementations always appearing on the market. For example, Cowray started shipping an OpenCL 1.2 on their intelligent embedded processors. Cadence is now shipping OpenCL on their Tensilica Vision DSP, and Google just shipped OpenCL 3.0 on their Tensor SoC. Khronos tracks the number of open source projects on GitHub using OpenCL as just one indicator of how widely OpenCL is being used throughout the industry. There are now close to 16,000 OpenCL related projects. That's almost a 4 times increase over the last 4 years, and the trend line is accelerating. The latest version of OpenCL is OpenCL 3.0 that was finalized and released in September 2020, so just a year ago. OpenCL 3.0 enables hardware vendors to focus their resources on driver functionality that their customers need by making all functionality beyond OpenCL 1.2 optional through API queries and language macros. OpenCL 3.0 also removed the OpenCL C++ language from the specification and recommends use of the C++ for OpenCL open-source front-end compiler that generates SPIR-V code. Existing applications can be easily moved to OpenCL 3.0. OpenCL 1.2 applications require no changes, and OpenCL 2.x applications also require no changes if their functionality they use is known to be present, but we do recommend for future portability to any OpenCL implementation that developers use queries for any optional functionality that they use. An increasing number of companies have adopted OpenCL 3.0 and will be able to ship implementations when they are ready. But actually ARM, Google, Imagination, Intel, NVIDIA, and VeriSilicon are already shipping conformant OpenCL 3.0 implementations, and I would expect that most OpenCL adopters will move to OpenCL 3.0 over time. The C++ for OpenCL Open-Source Front-end Compiler is supported in Clang. It leverages LLVM and generates SPIR-V code. C++ for OpenCL is fully compatible with OpenCL C and also enables developers to use most C++ 17 features in OpenCL kernels. The new CXX for OpenCL extension enables an OpenCL driver to ingest and compile kernels written in the C++ for OpenCL kernel language. The OpenCL working group is also expanding the OpenCL SDK, the software development kit, to increase its value to developers. This is an ongoing project, and any community contributions are very welcome. Our goal is an SDK with a comprehensive user guide and a set of samples that use the SDK headers and build system with full CI. Over time, we also intend to include utility libraries, and we are very interested in which libraries developers would find most useful. And most significantly, we already have a new loader that enables loadable debug layers for software development and debugging that are available today. So the OpenCL specification has regular maintenance updates, and there is a steady pipeline of extensions with new functionality. For example, in just the past year, Khronos has released extensions to enhance OpenCL's performance and flexibility across multiple platforms, including enhanced subgroup functionality and faster neural network inferencing. All of these OpenCL specifications, including the core specification and extensions, can be found on the OpenCL registry, and the link is there in the slide. So what are some of the most significant extensions over the last year? So OpenCL has just finalized a set of asynchronous DMA extensions to enable DSP-like embedded processors to transfer data between global and local memory using DMA transactions. This new functionality complements the previous one-dimensional operations by supporting complex memory transfers and by enabling multiple asynchronous transactions to run in parallel using fences for synchronization. In fact, this is just one extension. There is significant activity in continuing to extend OpenCL functionality for DSPs and other embedded processors. Also, by popular demand from developers, we have released a set of extensions for external memory sharing, which enables OpenCL to interop with other APIs, such as Vulkan, by importing handles to memory and semaphore objects, and then using semaphores to wait and signal the other runtime to coordinate the use of shared memory. So interop between OpenCL and Vulkan has been in strong demand on both mobile and desktop platforms, and these extensions will be used to interop to other APIs, such as DX12 today and more APIs in the future. So these interop extensions have been released provisionally, which means we welcome developer feedback before we finalize them. So if this is of interest, now please let us know what you think. The OpenCL Working Group also maintains a roadmap of possible upcoming extensions. Some of the most active discussions are around command buffer recording and replay, which will enable a command buffer to be recorded and then separately dispatched. So enqueuing the same workload multiple times from a recorded command buffer significantly lowers call overhead and execution latency. And this is particularly useful to increase the performance of use cases with many smaller commands, such as machine learning and inferencing. And actually, the hot off the press news is that this provisional command buffer extension is going to be released tomorrow in about 8 hours. But overall, we highly value input and feedback from the developer community on which extensions should be prioritized and whether any needed functionality is missing from the roadmap. Please give us requests and feedback on the OpenCL specification GitHub. We need to ensure that needed functionality is on the extension roadmap, as only extensions that are proven to be useful and widely adopted will be lifted into future core OpenCL specifications. So before I finish, let's look at some broader trends around APIs in the industry. For example, there is a growing industry practice of layering APIs over other APIs through the cross-compilation of shading languages. And this trend is continuing to grow. So for developers, a layered API can enable their application to run on platforms that don't support that API natively, reducing platform fragmentation. For example, we have an implementation of Vulkan that runs over Apple's Metal, so Vulkan applications can run on Apple platforms. Layered APIs can also be invaluable to platform vendors to enable additional content on their platform without incurring the support load of an additional kernel-level driver. This layering trend is being fueled by the increasingly robust open source compiler ecosystem leveraging Khronos' SPIR-V. And this is making SPIR-V an ever more central part of the Khronos standards family. So as we mentioned, SPIR-V is an intermediate language representation that includes heterogeneous parallel processing and graphics operations that can be broken down into instructions for GPUs and other processors. SPIR-V is the only language directly ingested by Vulkan, and it can be imported into a growing number of OpenCL implementations as well. SPIR-V enables the hardware and compiler communities to innovate independently, as front-end compilers can simply generate SPIR-V code to be ingested and executed by a wide range of runtime APIs. And in addition, API runtimes that ingest SPIR-V eliminate the need for front-end compilers to be shipped in the driver, which can be particularly important in smaller embedded systems. And here are two examples of layered OpenCL implementations. The Google CLSPV compiler on the left enables OpenCL kernels to be compiled and executed on a Vulkan runtime, which together with the CLVK runtime API translator enables OpenCL applications to run over Vulkan. CLSPV is already being used to ship demanding OpenCL applications on Android, such as Adobe's Rush video editor, that has over 200,000 lines of OpenCL C now running on Vulkan with full GPU acceleration. And Microsoft has now released the OpenCL on 12 open source project to layer OpenCL over Microsoft's DX12 API. With Collaborator's assistance, Microsoft leverages the Mesa open source graphics framework to translate SPIR-V through Mesa's near intermediate representation into DXIL, DirectX's intermediate language. It's amazing it all works. CL on 12 will enable accelerated OpenCL wherever Windows with DX12 ships, including on ARM-based PCs and in the cloud, and should soon be officially conformant. The last trend I'll mention today is about machine learning, which is one of the most significant markets driving the need for increased compute acceleration today. Many companies are researching and developing machine learning compilation stacks, and they all follow a similar design pattern. After applying graph-level optimizations to imported networks, the networks are decomposed into executable instructions. CPU code is handled through a compiler such as LVM for the CPU, and Vulkan or OpenCL code is also emitted by the compiler to portably access acceleration hardware. The widespread cross-platform availability of Vulkan to access GPU acceleration makes it an effective back-end target for deploying inferencing into runtime applications such as games. All Vulkan and many OpenCL implementations ingest SPIR-V, and that's making SPIR-V itself increasingly an attractive back-end compiler target for ingestion into hardware runtimes. So I hope that was a useful introduction, or maybe a refresher, to Khronos open standards for compute acceleration. All of the specifications we have mentioned are being actively developed to increase functionality and performance. For example, here are just some of the extensions in development for machine learning acceleration across the different working groups. But effective open standards always need to be listening to market needs, and the requirements and use cases from the RISC-V community can be very influential in helping to evolve these Khronos APIs, if we have a clear understanding of what we can do to help the RISC-V community. And so in my final slide, I would like to leave a thought that we may want to explore closer cooperation and communication between Khronos and RISC-V. For example, a liaison agreement between our organizations could let us more closely share use cases, requirements, and draft specifications for review and feedback. Khronos has many such liaisons with other organizations in the industry, and we would welcome discussions to establish such a relationship with RISC-V. So, thank you for your time today, and I hope this session can be the start of an even more productive ongoing relationship and dialogue between RISC-V and Khronos. Thank you.
Well, thank you for very meaningful the detailed explanation. So thank you for your good presentation. Yeah. So from audience, so no question about it. No question about the presentation. So I have some. So sorry, it's maybe a basic question, maybe, but
Yep.
So Khronos Group is also open source strategy. So open source basic idea. So it's so sometimes open source has some a kind of regulation or rule also. There's some interactive or some difference between open source community. So it's a Linux open source or also some other open source? Is it same rule, or kind of different integration has happened? Just a question.
Yeah, that's actually a very good question. So Khronos loves open source, but our primary product are open standard specifications, but we use open source to build the ecosystem around those specifications. And people often get open source and open standards confused. They are both very good, but it's important to understand when to use which one. And an open specification enables multiple implementations. So, for example, in the GPU industry, my own company, NVIDIA, we are just one company that builds GPUs, that implements the Vulkan API. And open standards are appropriate where you want to have multiple implementations. Multiple companies want to innovate their products, but underneath a standard API. Of course, open source is slightly different. Typically, you'd have multiple companies sharing resources to build a single implementation of a tool or library or an operating system. And that can be a very powerful way. If people don't want to compete on implementation, but they want to share implementation resources. So at Khronos, again, our primary product are these open specifications like Khronos and OpenCL, OpenVX. But all of the tooling that we build, and even the specifications documents themselves, are all in open source. So open source and open standards are very closely related, but they are quite different.
Okay. Oh, thank you for answering. So there are question from audience. So I will inform you. So the question is, isn't Caffe 2 now integrated into PyTorch? Sorry. Caffe 2 now integrated into PyTorch?
Good question. I think so. One of the interesting things is all of the machine learning frameworks are very rapidly innovating. It's a very interesting area. We're constantly asking the machine learning frameworks what acceleration they need. And it kind of changes over time. Sometimes they say they want high-level meta commands. Sometimes they say, just give us matrix multiplication and we'll compile down to that. But it is a very dynamic area. And there's a lot of research going on into the frameworks and compiler stacks. A lot of the frameworks want to use higher level commands today, but I think over time, as the compilers get better, probably, we'll see, I suspect, many of the frameworks will end up using the lower level commands, using their compiler stacks to reach into the hardware effectively. But it's a very interesting and dynamic area, and it's one we're paying a lot of attention to. So if anyone in the audience is building machine learning frameworks or compilers, we'd love to hear what your requirements are so we can provide effective acceleration.
Thank you. So, and there is another question from audience. The question is, are you aware of any Vulkan capable OSS GPU core implementation?
Open source GPUs? Was that the question?
going Vulkan C, the question person said.
Okay.
Open GPU. Oh, I'm
Okay.
not sure. Sorry. The question not doesn't say about
Yeah. So I am aware of some open source GPU designs, and the ones that I'm aware of are first targeting like IoT markets, I believe, where the performance requirements aren't as high as desktop gaming, but that's something that Khronos fully supports. They any GPU in open source or closed source is welcome to use any of our APIs, and hopefully having those API specifications being well defined with lots of conformance testing available in open source for free will enable any GPU implementation to be more cheaply produced and more quickly produced. So yeah, so Khronos, we would fully support any GPU implementation from any vendor, including open source projects.
So, question persons added that. So, Vulkan is a kind of OpenGL, but Vulkan, B-U-L-C-A-N. Yeah. Is some
Yeah.
is some implementation.
Yeah.
Yeah.
Sure. No, that's another good question. So we didn't cover 3D APIs so much in the slides, but I can summarize. So OpenGL was an API that will be available for many years. OpenGL is almost 30 years old as an API, and I expect it will be available for another 30 years. It's used by so many applications. All of the GPU vendors will continue to support OpenGL forever. But the hardware for 3D graphics is very different today than what it was with silicon graphics 30 years ago. Back then, it was a state machine. Now it's highly programmable and highly parallel. And so we needed a new generation API to enable developers to effectively use the power and the flexibility of today's GPU hardware. And that is what Vulkan is. It gives much lower level control over the GPU hardware. The application developer has much more control over what tasks are running, over memory allocation, all aspects of how the GPU is being used to accelerate their application. So that the way I like to explain it is OpenGL was really a 3D graphics API. Vulkan is really a GPU API to drive GPU hardware for both compute and all kinds of rendering operations. So if you're learning 3D graphics, Vulkan can be a little more complex to first learn because there's a lot more detail about modern GPUs. But most developers that I have talked to who have made the transition from OpenGL to Vulkan, they end up really liking it because they value the control, the extra level of control that Vulkan gives them for modern high performance, low latency 3D applications. So we are seeing most developers now transitioning from OpenGL to Vulkan, and I think that is a trend that will continue.
Oh, okay. So then Vulkan is more close to the hardware implementation. I think it's right. Yeah.
That is exactly right. Yeah, it's closer to the hardware, and you have more control. I mean, the NVIDIA OpenGL driver, and it is currently 5 million lines of code. There's a lot of code between you and the hardware if you're using OpenGL, and it's an awesome driver, but that sometimes and increasingly the developers they know what they want to do with the GPU acceleration better than any driver can possibly know, because every application is different. And so Vulkan gives them direct access to the hardware. So it's the modern way to do it.
Oh, I see. Oh, thank you. Thank you so much for answering questions. And
of course,
it's very close to the end of time. So can we get to the next session? So just a small break time. Yeah. Okay. Thank you so much for your great presentation.
Yep.
Yeah.
Thank you very much.
Thank you.